Inorganic Chemistry Quiz. For convenience, chemists use symbols of one or two letters to represent the elements. The first letter of a symbol is always capitalized, but any following letters are not. The symbols of some elements are derived from their Latin names. For example, Ag from argentum, Au from aurum, Cu from cuprum, Fe from ferrum, Hg from hydrargyrum, K from kalium, Na from natrium, Pb from plumbum, Sb from stibium, Sn from stannum, and W from wolfram. Whereas the symbols of most elements come from their English names. The three states of matter can be interconverted without changing the composition of the substance. Upon heating, a solid, for example, ice, will melt to form a liquid, water. The temperature at which this transition occurs is called the melting point. Further heating will convert the liquid into a gas. This conversion takes place at the boiling point of the liquid. On the other hand, cooling a gas will cause it to condense into a liquid. The temperature at which this transition occurs is called the condensation point. When the liquid is cooled further, it will freeze into a solid form. This conversion takes place at the freezing point of the liquid. All measurable properties of matter fall into one of two categories: extensive properties and intensive properties. The measured value of an extensive property depends on how much matter is being considered. Mass, which is the quantity of matter in each sample of a substance, is an extensive property. More matter means more mass. The values of the same extensive property can be added together. For example, two copper coins will have a combined mass that is the sum of the masses of each coin. And the length of two tennis courts is the sum of the lengths of each tennis court. Volume, defined as length cubed, is another extensive property. Dalton's work marked the beginning of the modern era of chemistry. The hypothesis about the nature of matter, on which Dalton's atomic theory is based, can be summarized as follows. Number one, elements are composed of extremely small particles called atoms. Number two, all atoms of a given element are identical, having the same size, mass, and chemical properties. The atoms of one element are different from the atoms of all other elements. Number three, compounds are composed of atoms of more than one element. In any compound, the ratio of the number of atoms of any two of the elements present is either an integer or a simple fraction. Number four, a chemical reaction involves only the separation, combination, or rearrangement of atoms. It does not result in their creation or destruction. According to Dalton's atomic theory, atoms of the same element are identical, but atoms of one element are different from atoms of other elements. Compound formed from atoms of elements X and Y. In this case, the ratio of the atoms of element X to the atoms of element Y is 2 to 1. This idea is an extension of Proust's law of definite proportions, which states that different samples of the same compound always contain its constituent elements in the same proportion by mass. Thus, if we were to analyze samples of carbon dioxide gas obtained from different sources, we would find in each sample the same ratio by mass of carbon to oxygen. Dalton's third hypothesis explains the law of multiple proportions quite simply. Different compounds made up of the same elements differ in the number of atoms of each kind that combine. For example, carbon forms two stable compounds with oxygen, namely carbon monoxide and carbon dioxide. Modern measurement techniques indicate that one atom of carbon combines with one atom of oxygen in carbon monoxide and with two atoms of oxygen in carbon dioxide. Three types of rays are produced by the decay or breakdown of radioactive substances such as uranium. Alpha rays consist of positively charged particles called alpha particles. Beta rays or beta particles are electrons and are deflected by the negatively charged plate. The third type of radioactive radiation consists of high energy rays called gamma rays. Like X rays, gamma rays have no charge and are not affected by an external field. The electron, the proton, and the neutron are the three fundamental components of the atom that are important in chemistry. The protons and neutrons of an atom are packed in an extremely small nucleus. Protons and neutrons are collectively called nucleons. Electrons are shown as clouds around the nucleus. Atoms of a given element do not all have the same mass. Most elements have two or more isotopes, atoms that have the same atomic number but different mass numbers. For example, there are three isotopes of hydrogen. One, simply known as hydrogen, has one proton and no neutrons. The deuterium isotope contains one proton and one neutron. And tritium has one proton and two neutrons. Recognition of periodic regularities in physical and chemical behavior and the need to organize the large volume of available information about the structure and properties of elemental substances led to the development of the periodic table, a chart in which elements having similar chemical and physical properties are grouped together. In the modern periodic table, elements are arranged by atomic number in horizontal rows called periods, and in vertical columns known as groups or families, according to similarities in their chemical properties. Of the 83 elements that are found in nature, 12 make up 99.7% of Earth's crust by mass. They are, in decreasing order of natural abundance, oxygen, silicon, aluminum, iron, calcium, magnesium, sodium, potassium, titanium, hydrogen, phosphorus, and manganese. Elements are often referred to collectively by their periodic table group number, group 1A, group 2A, and so on. However, for convenience, some element groups have been given special names. The group 1A elements are called alkali metals. The group 1B are called coinage metals. The group 2A elements are called alkaline earth metals. And the group 2B are called volatile metals. Elements in group 5A are known as pnictogens. Elements in group 6A are known as chalcogens. Elements in group 7A are known as halogens, and elements in group 8A are called noble gases or rare gases or aerogens. A molecule is an aggregate of at least two atoms in a definite arrangement held together by chemical forces, also called chemical bonds. A molecule may contain atoms of the same element or atoms of two or more elements joined in a fixed ratio in accordance with the law of definite proportions. Thus, a molecule is not necessarily a compound, by which definition is made up of two or more elements. Like atoms, molecules are electrically neutral. The hydrogen molecule, symbolized as H2, is called a diatomic molecule because it contains only two atoms. Other elements that normally exist as diatomic molecules are nitrogen and oxygen, as well as the group 7A elements, fluorine, chlorine, bromine, and iodine. Of course, a diatomic molecule can contain atoms of different elements. Examples are hydrogen chloride HCl and carbon monoxide CO. An ion is an atom or a group of atoms that has a net positive or negative charge. The loss of one or more electrons from a neutral atom results in a cation, an ion with a net positive charge. For example, a sodium atom can readily lose an electron to become a sodium cation, which is represented by Na positive 1. On the other hand, an anion is an ion whose net charge is negative due to an increase in the number of electrons. A chlorine atom, for instance, can gain an electron to become the chloride ion, Cl negative 1. An allotrope is one of two or more distinct forms of an element. Note that oxygen O2 and ozone O3 are allotropes of oxygen. Two allotropic forms of the element carbon, diamond and graphite, are dramatically different not only in properties but also in their relative cost. Many ionic compounds are binary compounds, or compounds formed from just two elements. For binary compounds, the first element named is the metal cation, followed by the nonmetallic anion. With the important exemption of the ammonium ion, all cations of interest to us are derived from metal atoms. Metal cations take their names from the elements. The anion is named by taking the first part of the element name and adding IDE. Oxoacids are acids that contain hydrogen, oxygen, and another element, the central element. The formulas of oxoacids are usually written with the hydrogen first, followed by the central element and the oxygen. Addition of one oxygen atom to the ic acid. The acid is called per-ic acid. Thus, adding an oxygen atom to HClO3 changes chloric acid to perchloric acid, HClO4. Removal of one oxygen atom from the ic acid, the acid is called ous acid. Thus, nitric acid, HNO3, becomes nitrous acid, HNO2. Removal of two oxygen atoms from the ic acid, the acid is called hypoous acid. Thus, when HbRO3 is converted to HbRO, the acid is called hypobromous acid. Hydrates are compounds that have a specific number of water molecules attached to them. For example, in its normal state, each unit of cupric sulfate has 5 water molecules associated with it. The systematic name for this compound is cupric sulfate pentahydrate, and its formula is written as CuSO4 times 5H2O. The water molecules can be driven off by heating. When this occurs, the resulting compound is CuSO4, which is sometimes called anhydrous cupric sulfate. Anhydrous means that the compound no longer has water molecules associated with it. Several common ionic compounds are classified as soluble or insoluble. Keep in mind, however, that even insoluble compounds dissolve to a certain extent. Soluble compounds are compounds containing alkali metal ions and ammonium ions. Soluble compounds are nitrates, acetates, bicarbonates, chlorates, and perchlorates. Soluble compounds are halides except halides of silver, mercury, and lead. Sulfates are soluble compounds except sulfates of silver, calcium, strontium, barium, mercury, and lead. Insoluble compounds are carbonates, phosphates, chromates, and sulfides, except compounds containing alkali metal ions and the ammonium ion. Hydroxides are insoluble compounds, except compounds containing alkali metal ions and the barium ion. Limestone and dolomite, which are widespread on Earth's surface, often enter the water supply. Calcium carbonate is insoluble in water. However, in the presence of dissolved carbon dioxide from the atmosphere, calcium carbonate is converted to soluble calcium bicarbonate. Water containing calcium and or magnesium ions is called hard water, and water that is mostly free of these ions is called soft water. Hard water is unsuitable for some household and industrial uses. Acids commonly used in the laboratory include hydrochloric acid HCl, nitric acid HNO3, acetic acid CH3COOH, sulfuric acid H2SO4, and phosphoric acid H3PO4. The first three are monoprotic acids. That is, each unit of the acid yields one hydrogen ion upon ionization. Certain salts like carbonates, bicarbonates, sulfites, and sulfides react with acids to form gaseous products. For example, the equation for the reaction between carbonates and acids forms carbon dioxide. Similar reactions involving other mentioned salts forms carbon dioxide, sulfur dioxide, as well as hydrogen sulfide. In free elements, that is, in the uncombined state, each atom has an oxidation number of zero. Thus, each atom in hydrogen molecule, bromine molecule, sodium metal, beryllium metal, potassium metal, oxygen molecule, and phosphorus molecule has the same oxidation number, zero. For ions composed of only one atom, that is, monoatomic ions, the oxidation number is equal to the charge on the ion. Thus, lithium ion has an oxidation number of positive 1, barium ion positive 2, ferric ion positive 3, iodide ion negative 1, oxide ion negative 2, and so on. All alkali metals have an oxidation number of positive 1 and all alkaline earth metals have an oxidation number of positive 2 in their compounds. Aluminum has an oxidation number of positive 3 in all its compounds. The oxidation number of oxygen in most compounds, for example, magnesium oxide and aluminum, is negative 2. But in hydrogen peroxide, H2O2, it is negative 1. The oxidation number of hydrogen is positive 1, except when it is bonded to metals in binary compounds. In these cases, for example, lithium hydride, sodium hydride, calcium hydride, its oxidation number is negative 1. Fluorine has an oxidation number of negative 1 in all its compounds. Other halogens, chlorine, bromine, and iodine, have negative oxidation numbers when they occur as halide ions in their compounds. When combined with oxygen, for example in oxoacids and oxoanions, they have positive oxidation numbers. In a neutral molecule, the sum of the oxidation numbers of all the atoms must be zero. In a polyatomic ion, the sum of oxidation numbers of all the elements in the ion must be equal to the net charge of the ion. Oxidation numbers do not have to be integers. For example, the oxidation number of oxygen in the superoxide ion O2 negative 1 is negative 1 half. The formation of the shell of a hen's egg is a fascinating example of a natural precipitation process. An average eggshell weighs about 5 grams and is 40% calcium. The eggshell is largely composed of calcite, a crystalline form of calcium carbonate. Normally, the raw materials, calcium ions and carbonate ions, are carried by the blood to the shell gland. The calcification process is a precipitation reaction. In the blood, free calcium ions are in equilibrium with calcium ions bound to proteins. As the free ions are taken up by the shell gland, more are provided by the dissociation of the protein-bound calcium. The carbonate ions necessary for eggshell formation are a metabolic byproduct. Carbon dioxide produced during metabolism is converted to carbonic acid by the enzyme carbonic anhydrase. Carbonic acid ionizes stepwise to produce carbonate ions. When a neutral atom is converted to an ion, we expect a change in size. If the atom forms an anion, its size or radius increases because the nuclear charge remains the same, but the repulsion resulting from the additional electrons enlarges the domain of the electron cloud. On the other hand, removing one or more electrons from an atom reduces electron-electron repulsion, but the nuclear charge remains the same. So, the electron cloud shrinks, and the cation is smaller than the atom. Any questions? If there is any, kindly post it on the comment section. I hope you have learned something today. Thank you for listening.